In question number 16, parallel monochromatic beam of light is incident normally on a narrow slit. A diffraction pattern is formed on a screen placed perpendicular to the direction of incident beam. At the first maximum of the diffraction pattern, the phase difference between rays coming to the edges of the slit is. We want to find the phase difference at first maximum. Here the phase difference is given by 2 pi by lambda into d sine theta. The first minima of the diffraction pattern occurs at sine theta is equals to lambda by d. So phi will be written as 2 pi by lambda into d and sine theta is lambda by d. So phi will be equal to 2 pi. So option D is correct option. In question number 17, red light is generally used to observe diffraction pattern from single slit. If blue light is used instead of red light, then what will happen to diffraction pattern? Here the fringe width is given by lambda capital D upon small d. So fringe width is directly proportional to lambda, as lambda for blue light is less than lambda for red light, the fringe width will decrease. So the diffraction pattern will contrast. So option B is correct option. In question number 18, a plane wavefront of wavelength 6 into 10 power minus 7 meter falls on a slit 0.4 mm wide. A convex lens of focal length 0.8 meter is placed behind the slit, focuses the light on the screen. We want to find the linear diameter of second maximum. Here for secondary maxima, d sine theta is given by phi lambda by 2. So d into theta, because sine theta can be written as approximately theta, is equals to d into x by capital D, that is equal to phi lambda by 2. So 2 into x will be equal to phi lambda, capital D is here focal length, divided by D, that is equals to phi into the lambda is 6 into 10 power minus 7, focal length is 0.8 meter and slit width is 4 into 10 power minus 4 meter. So simplifying this, we will get answer is equals to 6 mm. So option A is correct option. In question number 19, to observe the diffraction, the size of an obstacle should be of the order of wavelength. The slit width should be comparable to the wavelength. So option A is correct option. In question number 20, a slit of size 0.15 centimeter is placed at distance 2.1 meter from a screen on illuminated by a light of wavelength 5 into 10 power minus 5 centimeter. We want to find the width of central maxima. Width of central maxima is given by 2 lambda capital D upon small d, that is equals to 2 into 5 into 10 power minus 5 into 2.1 divided by 0.15 into 10 power minus 2. Simplify this, we will get lambda is equals to, we will get 2 beta, the fringe width central maximum is equals to 1.4 mm. So option C is correct option. In question number 21, angular width of central maximum of diffraction pattern on a single slit does not depend upon. The angular width 2 theta is given by 2 times sine inverse of lambda upon small d. Here lambda is the wavelength and d is the slit width. So it is independent of capital D, that is the distance between slit and source. So option A is correct option. In question number 22, the radius r of half period zone is proportional to. The radius of half period zone is given by under root and d lambda. Here n is the number of period zone, so Rn is directly proportional to root n. So option A is correct option. In question number 23, we want to find the width of nth half period zone. The width of nth half period zone is given by Rn minus R of n minus 1. Rn is given by under root n d lambda or n b lambda as given in the options, and Rn minus 1 is given by under root n minus 1 into b lambda. Taking root b lambda common, we can write under root b lambda into root n minus root of n minus 1. So option B is correct option. In question number 24, the condition for observing Fraunhofer diffraction from a single slit is that the light wavefront incident on the slit should be, the light wavefront should be plane wavefront. So option C is correct option. In question number 25, a single slit of width A, A is slit width, is illuminated by violet light of wavelength 400 nanometer, that is 4 into 10 power minus 7 meter, and the width of diffraction pattern is measured as y. So y will be width of diffraction pattern. The half of the slit width is covered and illuminated by yellow light. The half is covered by yellow light of wavelength, let's say lambda dash, that is 600 nanometer. So 6 into 10 power minus 7 meter. we want to find what will happen to the width of diffraction pattern. The width of central maxima y is given by 2 lambda capital D upon small d. Here capital D and small d are constant, so we can write y is directly proportional to lambda. So y dash by y will be equal to lambda dash upon lambda. So y dash upon y will be equal to lambda dash is 600 nanometer, that is 6 into 10 power minus 7 upon lambda. Lambda is given 4. So 4 into 10 power minus 7. But in this case, the slit is half covered compared to first. So slit width is not constant. So y is inversely proportional to slit width d. So y dash by y will be proportional to also d upon d dash. So into d divided by d dash is d by 2. So simplifying this, we will get y dash by y is equals to 3. So y dash is equals to 3y. So option C is correct option. In question number 26, a diffraction is obtained by using a beam of red light. Now what will happen if the red light is replaced by the blue light? Here the width is given by lambda capital D upon small d. So beta is directly proportional to lambda. As lambda of blue is less than lambda of red, the fringe width will decrease. So the bands will be narrower and crowd full together. So option A is correct option. In question number 27, if we observe the single slit Fraunhofer diffraction with wavelength lambda and slit width E, here the slit width is given E. The width of central maxima is 2 theta. On decreasing the slit width for same lambda, what will happen to the central maxima? So we are decreasing the slit width. Here 2 theta, that is central maxima, is given by 2 lambda divided by d. Here slit width is given as E. So if slit width is decreasing, the 2 theta or theta will increase. So theta will increase. So option A is correct option. In question number 28, in the far field diffraction pattern of a single slit under polychromatic illumination, the first minimum with the wavelength lambda 1 is found to be coincident with the third minimum at lambda 2. So first minimum of lambda 1 is coincident with the third minimum of lambda 2. So we want to find the relation between lambda 1 and lambda 2. So the position of first minimum is equals to position of third minimum. The position of first minimum is given by lambda 1 d divided by capital small d is equals to third minimum is given by 2 into 3 plus 1, because it is 2n plus 1, divide by 2 into lambda 2 d by small d. So lambda 1 will be, this will get cancelled out, 7 by 2 lambda 2. So lambda 1 is equals to 3.5 lambda 2. So option C is correct option. In question number 29, a light wave is incident normally over a slit of width d is equals to 24 into 10 power minus 5 centimeter. The angular position of second dark fringe from central maxima is 30 degree. It is the position of second dark fringe. We want to find the wavelength of light. For the second dark fringe, the condition is d sine theta is equals to 2 lambda. Here d is 24 into 10 power minus 5 into sine 30 degree is equals to 2 lambda. So 24 into 10 power minus 5 divided by 2, and sine 30 is half, that is equal to lambda. So lambda will be equal to 6 into 10 power minus 5, but this will be in centimeter. So lambda is equals to 6 into 10 power minus 7 meter, that is equals to 6000 angstrom. So option A is correct option. In question number 30, a beam of light of wavelength 600 nanometer from a distant source falls on a single slit 1 mm wide, and the resulting diffraction pattern is observed on a screen 2 meters away. We want to find the distance between first dark fringe on either side of the central bright fringe. Here, the distance between first dark fringes will be twice of the position of central maxima or the width of central maxima. So that will be equal to width of central maxima, because if we see the diffraction pattern, if this is the central bright, then this will be first dark on either side. This is central maximum, and these are first dark. So distance between first two dark is equals to width of central maxima. The width of central maxima is given by 2 lambda capital D upon small d, that is equals to 2 into 6 into 10 power minus 7 into d is capital 2 divided by 1 mm, that is equal to 10 power minus 3. So the distance will be equal to 2.4 millimeter. So option D is correct option.